Valence bond theory. Remember valence bond theory from Chem 1A? You might want to review that for the final. So we can describe the bonding in complex ions using valence bond theory. So what we looked at there was if we have a linear geometry, that means we have two electron groups. And so we're going to take two orbitals and hybridize them to make them the same. Those orbitals would be one s and one p, and we average them essentially, mash them together. So this is then a sp hybridization, and we've got one on each side. Tetrahedral has four groups. So you take four orbitals and mash them together. So you've got the s and three p's, and then you've got four identical orbitals, and they're going to arrange themselves in a tetrahedral shape to maximize the space. If you have square planar, here you're going to have sp2d. Now this is a little different than what we saw in Chem 1A. That's going to make this shape. And then the octahedral, this is the same as what we saw in 1A. sp3d2 will make an octahedron. So the coordinate covalent bond that's made in these complex ions is the overlap between a completely filled atomic orbital and an empty atomic orbital. So the empty orbital is on the metal ion. So the metal ions hybridize according to the geometry of the complex ion. So we can have a metal ion with empty hybrid orbitals that are just here waiting for someone to come and share an electron pair. So valence bond theory explains the geometry of these complexes, but it doesn't explain other things like the different colors that they have and the magnetism. Some of them are magnetic and some are not. So complex ions form because of the attractions between the electrons on the ligands and the positive charge on the ion. Ligand electrons can also repel the metal electrons that are in unhybridized d orbitals. In an octahedral shape, we've got ligands overlapping with two d orbitals, which increases their energy more than the three d orbitals that are not included. Those fall between the ligands. So this is what we're talking about here. So this is called d orbital splitting. So on a free atom without any hybridization, you've got 5 d orbitals and they're degenerate. They have the same energy. When we bring those into hybridization, then we can have them overlap different ways. So, just orient myself here. So here we have the different ligands. This is on an octahedral complex. And then it's using 2 of the d orbitals, because this is going to be sp3d2. It's going to use 2 of the orbitals, d orbitals, and the other 3 are just left empty and unhybridized. So here's an unhybridized orbital. Let me back that up. That's not what we're doing. We have the ligands, and we're looking at d orbitals on the free atom. None of these are hybridized. So here we've got the ligands, the octahedral shape, in the same position for all 5 d orbitals. One of the d orbitals is this weird donut kind of shape. The others are all looking like four balloons. This one's horizontal, and these are all at angles. So the way it works out here is that for this orbital, it's going to line up with the ligands on each side. Well, that's going to be higher in energy. And here, these guys are going to line up with the ligands. The ligands overlap with the orbital lobes. That increases the energy because there's repulsion there. It's like, you're in my space. Here, the other three d orbitals are able to fit in between the ligands, and so there's weak repulsion. And so this is lower energy. So these three are going to be lower in energy than those two. This difference in energy is called the crystal field. Questions? This is weird. I know it's weird. Do you see how these guys are lining up differently? These match up with the ligand and these do not. So these are getting in the way of each other, they're repelling each other, so it's higher energy. So the crystal field splitting energy is the difference in energy between those split d orbitals. And how much they are split, the size of that splitting, will depend both on the ligand and the metal ion. So we have strong field complexes and weak field complexes. In strong field complexes, the splitting is large. The difference in energy is large. In weak field complexes, the splitting is small. So solutions of complex ions have often brilliant colors. And in our lab practical that we did, the group C ions were forming complex ions. And so we saw colored solutions, right? The manganese also did that. We saw a colored solution rather than a precipitate. Well, the color of the solution is related to the absorption of light by the electrons in the solution. So if all of the light was absorbed, it would appear black. Black color absorbs all wavelengths. White transmits or reflects all wavelengths. Any given color is going to reflect that we're absorbing some colors and reflecting others. So in a red solution, the red color is reflected or transmitted, and the other colors are absorbed. So we don't see those, we just see the red that's transmitted or reflected. And here we see the blue. And it's not, we're not limited to just primary colors here. You can have different combinations and lots of different colors based on which particular wavelengths are absorbed or reflected. So the color that we see ends up being a complementary color. So here we have a solution of hexa, aqua, titanium 3. It's going to be purple because it's absorbing on the other side of the color wheel. So when these colors are absorbed, then we see the colors on the other side. We can use spectroscopy to measure what wavelengths are absorbed. And this is what we did with our first real experiment. Remember, we had the little spectrometer and we measured the absorbance, right? So here what they're doing is they're scanning the wavelength, measuring the absorbance at different wavelengths. And here we see that there's a lot of absorption in the green and the yellow, right? And there's not very much out here in the red and the purple. So we're getting a lot of color, a lot of wavelengths in here that are absorbed. So these are the ones that we see because they're transmitted. So that the color that you see is complementary to what it's absorbing. We can calculate the crystal field splitting based on the wavelengths of light that are absorbed. So the photon energy is equal to Planck's constant times the frequency, which is also equal to Planck's constant times the speed of light over the wavelength, and that is equal to the crystal field splitting energy. So we can look at what color something is and get an idea of what the crystal field splitting energy is. Because this is going to be absorbing, like over here in the 560 nanometers. And so we can calculate the energy of the photons. So the complex ion, cobalt, NH35NO2, 2+, is yellow. Estimate the crystal field splitting energy in kilojoules per mole for this ion. So this complex ion is yellow. What color is it absorbing then? Purple. If we're seeing yellow, that's because it's absorbing purple. So we don't want to do a range because then we have to calculate twice. We're just going to pick one in the middle here, so halfway between 400 and 415 nanometers. So this is absorbing 415 nanometers. So the crystal field is equal to Hc over lambda. So H is Planck's constant. Dang it. Blanking on it. Hang on. .63 times 10 to the minus 34. 6.63 times 10 to the minus 34 joule seconds. And c is the speed of light, which is approximately 3 times 10 to the 8th meters per second. And then we're going to divide by the wavelength, 415 nanometers. We need to look at the units, right? So here we have seconds and seconds. Those are going to cancel out. Here we've got meters on top and nanometers on the bottom. That's not going to cancel. So we want to convert this into meters so the units are going to work out. Otherwise, our answer is going to be off by multiple factors of 10. So you could do that separately, or you can just say, well, I know that nano stands for times 10 to the minus 9. So instead of nano, I'm going to write times 10 to the minus 9 meters. It's not proper scientific notation. Your calculator doesn't care, right? So now we get the meters canceling out. So we do the math, and bury my calculator here. 6.63 times 10 to the minus 34 times 3 times 10 to the 8th divided by 415 times 10 to the minus 9. And this is going to give us 4.79 times 10 to the minus 19 joules. Now this is asking for crystal field splitting energy in kilojoules per mole. We found this amount of energy. How many particles is that for? That's one photon. That's one particle, right? So if we want to know what's the energy for a mole of particles, what do we need to do? So this is per one particle. Well, we want to get moles down here, and so multiply by particles, so the units cancel out. What number gives us the relationship between the mole and number of particles? Avogadro's number. 6.022 times 10 to the 23rd particles per 1 mole. Multiply by 6.022 times 10 to the 23. And that gives me a really big number. And that reminds me, oh yeah, they wanted it in kilojoules. So let's tack that on here. We want kilojoules. We have joules. We want those to cancel out. Kilo represents times 10 to the positive 3. So 1 times 10 to the 3 joules is equal to 1 kilojoule. And so this is going to give me an answer of 289 kilojoules per mole. Questions? And the tricky thing here is, they'll tell you what color the thing is, and you need to look on the opposite side to see what it's absorbing. Oops. So the ligands affect the magnitude of the splitting. So there's a spectrochemical series that lists the ligands in order of their ability to split d orbitals. So cyanide typically is going to give you a large splitting. So these are called strong field. And then as we go, they get lower and lower and lower, and iodide does not split the field very much, and so that's a weak field. Then the metal ion also has an effect. If it has a higher charge, it's going to pull the ligands in closer. And when the ligands are closer, then the repulsions are greater. So two things affect the magnitude. The charge on the metal, higher charge is going to give us more repulsion, larger crystal field. And then whether you have a strong field or a weak field ligand. So the magnetic properties, you have to remember Hund's rule. So Hund's rule says that when electrons fill degenerate orbitals, they're going to each take their own orbital, if possible, before they pair up. In the hotel analogy, this is two guys coming into a hotel room where there's 3 beds. Are they going to sleep together in the same bed? No, they're going to take their own beds, right? It's just natural. Or getting on the bus. You're not going to sit next to someone if there's a double seat open. You're going to take your own, right? So when the d orbitals get split, the lower energy orbitals fill first. Once they get half filled, there's a choice. You can pair up with an electron in one of those orbitals, or you can go higher in energy and get an empty orbital. And the decision that's made there is based on the size of the crystal field. So if the splitting is big, the electrons are like, yeah, it's not worth it to spend the extra energy to go up there. I'll just pair up with somebody and call it good. If it's a small difference, they're like, yeah, heck, I'm going to go up there and get my own space. Okay, so FeCN6 is known to be diamagnetic. Diamagnetic means all the electrons are paired up. The way I remember this is think about Noah's Ark, and the animals went in 2 by 2. They're all paired up, diamagnetic. And so here we have cyanide is a strong field ligand, and so the splitting here is large. So as we put the electrons in here, it has 6, 1, 2, 3, you're like, I don't want to make that leap, I'm going to just pair up, and they'll all be paired up, and we get a diamagnetic thing that is not going to interact with an electric field. Whereas FeH2O6 2+ is paramagnetic, it contains unpaired electrons. Now, para is not spelled the same way as pair. It does not mean pairs of electrons. So di is 2 by 2. This is the other. So water is a weak field ligand, and so this difference is small. So then the electrons come through and they go 1, 2, 3. Oh, I'll just take this small leap, 4 or 5 to have my own orbital. And then number 6 ends up pairing up down here. So we get unpaired unpaired electrons. This will interact with an electric field, a magnetic field, this one will not. So in general, complexes that have strong field ligands have fewer unpaired electrons. These are called low spin complexes. Whereas when we have weak field ligands, the splitting is lower, and these are going to be called high spin complexes because they're going to have the same number of unpaired electrons as the free metal ion. Only D4, 5, 6, and 7 metal ions have low and high spin possibilities. If you only have 3 electrons, right? If you only have 3 electrons in the D, 1, 2, 3, there's no choices to be made, right? It's only when you get to that 4th one that you could have a difference. So 1, 2, or 3 electrons there's not going to be any low or high spin. It'll all just be the same. Okay, how many unpaired electrons are there in the complex ion FeCl6 3-? Well, the first thing we need to know is how many d electrons are on that iron ion. So we need to know the charge on the iron. So we've got 6 chlorides, right? So they're -6. Overall, the charge is -3. What's the charge on iron? +3. So this has lost 3 electrons. So then we have to look at the electron configuration for iron. So that's going to be argon. And then after argon, we get 4s2, and 4s2, and 3d, how many? 1 for the scandium, 2, 3, 4, 5, 6. 6 electrons. Okay? That is an iron atom. Here we have, so that's just Fe. We want Fe 3+. What electrons is it going to lose? Which ones go first? The S's. Those go first, and then we're going to take some of those guys. So we'll totally lose the S, and we end up with 3D. So that was 2, and we need to take one of these. So 3D5. So iron 3+ has 5 electrons. And then we're going to look at that splitting. So we're going to have 3 low and 2 high. And when we go to put the electrons in here, we go 1, 2, 3, and then the 4th one needs to make a choice. Am I going to pair up with this guy, or am I going to go up there? And that's going to depend on how big the energy difference is. So this energy difference is that crystal field. So we're going to look at our ligand here, and we need to identify, is this a strong field or weak field? And I don't have that memorized, and you shouldn't bother trying to memorize it either. We're going to go look at the list. Right here. So here's chloride. This is small, weak field. So this is a small difference. So if this is a small difference, is this next electron going to go up there and have his own place? Yeah. Because they don't like sharing. Not if you can have your own bed, right? And then the other guy will go up there too. So 5 electrons, and they're all going to get their own. So how many unpaired electrons do we have? 5 unpaired. This is the kind of question that might show up on that take-home exam. How many unpaired electrons in the complex ion COCN6? 4 minus. Well, again, first we have to look at the metal ion. We need its charge. So here we have 6 cyanides, that's minus 6, and the overall charge is 4 minus, so this one must be plus 2. So then we'll look at cobalt is also going to be argon, 4s2, 3d7. It's got one more electron. So then if we look at cobalt 2 plus, we need to lose 2 electrons. It's just going to be those s electrons. 3d7. So we got 7 electrons. And then we look at the low and the high. Right, and this difference is the crystal field. And we start putting the electrons in. 1, 2, 3. Well, we need to know high field, strong field or weak field. So the cyanide. Again, we're going to go back and look at the list. Oh, cyanide's up here. This is big split, right? So is this 4th electron going to go up there? No, it's going to cost a lot of energy. So it's going to go in here. So there's 4, 5, 6, and then this guy has to go up there. So for this one, we have 1 unpaired electron. Any questions? Yeah. How did I know that this one had a smaller? It's because of the ligand. So this one was chloride, and this one's cyanide. And so we go look at that series, and we see that cyanide does a strong field split and makes a big energy difference, and chloride makes a smaller one. Any other questions? The splitting pattern is different for other geometries. So for tetrahedral and square planar, it's going to be different because of the different geometry. So here, when we have the tetrahedron and we look at how the d orbitals interact, we're going to have 2 that fit between the ligands and 3 that are going to conflict with the ligands. And so we have 3 high and 2 low. So the splitting is opposite. In square planar, it's more complex. We end up with 2 lows, and then these guys split as well, so a lot more complicated. These are almost always low spin, which means they're going to have fewer unpaired electrons.